The next topic for us in this overall topic of cardiac physiology is to talk about the electrical activity of the heart, specifically the action potentials that we see in two different cell types that we find in the heart. And these action potentials are similar, very much similar to the generic action potential that we studied previously, but there are some key differences. So first off, let's talk about the two different cardiac cells. The vast majority of the heart is made up of heart muscle, cardiac muscle. These cells, 99+% of the total mass of the heart, are these myocardial cells or contractile muscle cells. The other type of cell that we find in the heart are a class of cells that we call autorhythmic cells. They're very similar to neuronal cells when they're found in the heart. And these cells, we call them autorhythmic because they are pace setter cells. They have a very particular kind of action potential that allows them to actually generate action potentials spontaneously at some particular frequency. So without any external stimulation, these autorhythmic cells are able to generate action potentials at a particular frequency, meaning a particular number of action potentials per minute. Okay? So we're going to look at these two different cells and the different action potentials that we see in each of these cells. So first, let's look at the action potential that we see in the cardiac muscle tissue. Okay, so these are the cardiac myocardial cells, the muscle cells. The action potential that we see in these cells, these are not the spontaneously firing cells. They do require stimulation. Okay. The action potential that we see in these cells is divided up into several phases. Okay. And when one of these cells is sitting at resting potential, okay, it's described as being in the phase 4. Okay. For some reason, it starts off with 4. So whenever the cell is at resting membrane potential, it's in phase 4. Okay. The first change, the rising depolarizing phase, okay, the rising depolarizing phase is described as phase 0. So phase 0, we have rapid depolarization, so the membrane potential is becoming less negative, more positive. And this fast depolarization phase is similar to the fast depolarization phase of the generic neuronal action potential. Okay? Because it's due to the opening of sodium channels, the voltage-gated sodium channels that we studied previously. Okay? So the cell is sitting at resting membrane potential, and then it gets triggered. Okay? It gets some sort of external trigger that causes the membrane potential to depolarize, and then that opens the voltage-gated sodium channels. So sodium is rushing into the cell in phase 0, okay? And we know that those sodium channels are not open for very long, right? They tend to open and they kind of flicker shut. So phase 1 of the cardiac action potential is this little blip where the membrane potential reaches a peak and then it comes down slightly. It doesn't go all the way down, but it comes down slightly. So in this phase 1, that is caused by the closing of those voltage-gated sodium channels. But instead of going into a rapid repolarization phase, right, that we've studied before, instead the cardiac action potential enters a plateau phase, okay, where it stays depolarized for a given amount of time. This phase is called the phase 2. And phase 2, or the plateau phase, there's two things happening that's keeping the membrane potential depolarized. we have potassium ions moving out of the cell. Okay? We have potassium ions moving out of the cell, but we also have calcium ions moving into the cell. So around the time where those sodium channels were closing, we actually opened a voltage-gated calcium channel. Okay? So around the time where those sodium channels were closing in phase 1, we had actually the opening of voltage-gated calcium channels and voltage-gated potassium channels. And in phase 2, calcium moves into the cell, which would tend to depolarize the cell, but potassium at the same time is moving out of the cell, and that alone would tend to repolarize the cell. So those two positively charged ions moving in different directions causes this plateau phase that we see in phase 2. Okay. Now, eventually, the plateau ends, and we go into a repolarization phase. We go into phase 3. Now, phase 3 happens when those calcium channels close. So those calcium channels are open for a given amount of time, and then they close. And when they close, the potassium continues to move out of the cell, which causes this repolarization, this phase 3. Okay. And then the cell goes back to resting, phase 4. So in the cardiac action potential, we go from resting phase 4, something triggers the cell to depolarize, we open voltage-gated sodium channels, you get this rapid depolarization phase, phase 0. Okay. Those sodium gates close, which causes this blip in phase 1. And around that time, voltage-gated calcium channels and voltage-gated potassium channels open. They both open. Calcium moves into the cell, potassium moves out of the cell, and that creates the plateau phase of phase 2. After a given amount of time, calcium channels close, potassium continues to move out of the cell, which causes the repolarization phase, or phase 3. And the cell returns to resting membrane potential, phase 4. So that's what happens in the cardiac action potential. So the big difference here compared to our previous action potential that we've studied is the introduction of the calcium, voltage-gated calcium channels that create this plateau phase. Okay? And so you notice that a cardiac action potential is wider, right? Which means that it spends more time in this depolarized state than the previous action potentials that we've studied. Now there is a purpose to this. There is a purpose to having the cell sustain this depolarization. You remember these cardiac muscle cells are electrically coupled to one another, and the purpose is to get them all to fire action potentials at roughly the same time so that they can contract at the same time. And so having a wider or longer action potential gives neighboring cells enough time for this action potential to spread throughout the neighbors, and so they all fire at the same time and they all contract at the same time. Okay? So it allows for some cooperation between cardiac muscle cells. The autorhythmic cells. Okay? So I told you that something is stimulating these cardiac muscle cells to go into phase 0. Okay? And what's stimulating these cardiac muscle cells are the autorhythmic cells. The autorhythmic cells are responsible for keeping the pace of stimulation throughout the heart. So these autorhythmic cells are spontaneously active cells. They fire action potentials without the need of external stimulation. Okay? and they fire it at some particular frequency. And as we'll study in just a second, there are different groups of autorhythmic cells in the heart, and each one tends to fire action potentials at a particular frequency. So as we see here with this action potential, if we just look at what it looks like, okay, the first thing you might notice is the autorhythmic cells are really never sustaining a resting membrane potential. Okay? There's no period of time, of any length of time, where their membrane potential stays put, right? They have a very an ever-changing membrane potential. But the lowest value, as it's drawn on this slide, is -60. Okay? So these autorhythmic cells spend a brief time at -60, and then their membrane potential seems to be drifting in this upward depolarizing direction. Okay? Eventually they hit some sort of threshold potential, and all of a sudden they fire this action potential. They depolarize, fast depolarization, and then the fast repolarization. Okay? And then again, they spend a brief period of time at -60, and then they slowly start to depolarize again until they hit threshold again. Okay? So that's the behavior of these autorhythmic cells. So what is causing this, this pattern of activity? So first off, the cell is spending a brief time at -60. And when it's in this position, when the cell is at -60, what's going on here is that the cell has none of these voltage-gated ion channels are open. Right? At this point, none of the voltage ion channels are open, voltage-gated ion channels. But this autorhythmic cell has leak or passive channels that allow sodium to move into the cell. Okay? And the cells that we've studied before tend to be actually very impermeable to sodium at rest. They have very few or very, very few leak sodium channels. But these autorhythmic cells have more of these leak sodium channels. And so this is what causes the slow depolarization, or the slow shifting of membrane potential toward threshold. Okay? So the cell is briefly at -60, and then as sodium trickles into the cell, because there are all these leak channels, it slowly depolarizes, and it slowly moves closer and closer to threshold. When the membrane potential gets within a few millivolts, right, within a few millivolts to threshold potential, when it gets close, there is an opening of a voltage-gated calcium channel. This voltage-gated calcium channel is called the T-type, or the transient calcium channel. And it's called transient because these calcium channels, they just flicker open and closed. Okay? They just flicker open and closed. They let just a trickle of calcium into the cell. And that is enough to get the cell from a few millivolts away from threshold and then quickly up to threshold. Okay? And then once the cell hits threshold, there is another kind of voltage-gated calcium channel that opens. It's called the L-type, or the long-type calcium channel. And it's called the long type because it stays open for longer. So these calcium channels open and calcium flows into the cell, and that's what causes the rising phase of this action potential. And then right around the peak of the action potential, those calcium gates close, and we get the opening of our potassium channels that we know and love. Okay? These voltage-gated potassium channels. And so potassium flows out of the cell and the cell repolarizes down back to that -60. Okay? And so again, it doesn't stay at -60 very long because it has all these leak channels for sodium. And so the sodium starts trickling in, the cell starts to slowly depolarize, okay? And then eventually, as it gets a few millivolts away from threshold, we are opening our transient calcium channels, okay? Calcium flickers in, it pushes us to threshold, and then once we're at threshold, we open the L-type calcium channels, the long calcium channels, and that causes a rush of calcium into the cell and a rapid depolarization. And then right around the peak of this action potential, calcium channels close, we open the potassium channels, and then the potassium leaves the cell and causes the rapid repolarization of the cell. And so this is happening over and over and over again. And this is what creates this autorhythmicity, this spontaneous firing of action potentials. The autorhythmic cells are scattered throughout a particular locations within the heart. Okay? And these autorhythmic cells are also connected to each other through fibers that are similar to the neuronal axons that we've studied in the nervous system. So the autorhythmic cells, there's a collection of autorhythmic cells at what's called the sinoatrial node or the SA node. This is located within the right atrium, okay, within the right atrium, close to where the blood enters from the superior vena cava. So that's the SA node. And then we have another group of autorhythmic cells that occupy a space that's called the atrioventricular node or the AV node. And the AV node is located almost at the center of the heart. It's located near the septum, where in between the atria, in between the right and left atria, and also it's located above the ventricles. So we have the AV node, and as you can see, the SA node is connected to the AV node with these fibers that I'm describing. Okay. The SA node is also connected to, which SA node in the right atria is connected to the left atria through these fibers. Okay. The AV node, okay, there's also another collection of autorhythmic cells that are found in a space in the heart called the intraventricular septum. It's this muscle that is sitting in between the ventricles. And we have two branches of collections of autorhythmic cells called the left and right branches of the bundles of His. Okay. So the left and right branches of the bundles of His that occupy this intraventricular septum is another group of autorhythmic cells. And they are connected to the ventricular muscle through a network of fibers called the Purkinje fibers. And so you can see these Purkinje fibers penetrate the right and left ventricular muscle. Okay. And so the action potential can spread very quickly to this muscle through these fibers. So three primary locations, the SA node, AV node, and the left and right branches of the bundles of His, okay, which are also associated with the Purkinje fiber system. So these three locations tend to fire action potentials at different frequencies. Okay. The SA node tends to fire action potentials between about 70 to 80 action potentials per minute. The AV node fires about 40 to 60 action potentials per minute, And the bundles of His and Purkinje fibers, the bundles of His fire about 20 to 40 action potentials per minute. So as you can see, the SA node has the fastest natural firing rate. Okay? The SA node has the fastest natural firing rate. Now the differences between these firing rates or firing frequencies is really all about the duration of this slow depolarization phase. Okay? So for some cells like the SA node, they tend to depolarize from that -60 up to threshold more quickly, and so they can fire more action potentials in a minute, compared to cells like the bundles of His that take longer to go from that -60 to threshold, and so they fire fewer action potentials per minute. So the SA node is often called the pace setter of the heart, or the pacemaker of the heart, because it is actually going to set the heart rate, or the firing rate of the entire heart, because it has the fastest natural firing frequency. Okay? Basically, it's going to fire an action potential before the other groups of cells get a chance to, and as soon as it fires an action potential, that action potential quickly spreads to the rest of the system, okay? The rest of this conduction system. So the cardiac action potential is going to actually start in the SA node. Okay? And once the SA node fires an action potential, it quickly spreads in two directions at once. It spreads to the left atria through this, what we call the interatrial pathway. That's the fibers that connect the SA node to the left atria. And it's also going to go through what's called the internodal pathway, which are the fibers that connect the SA node to the AV node. Now, once the SA node fires an action potential, the AV node is also then going to fire an action potential, but it's not instantaneous. The AV node fires an action potential about 100 milliseconds after the SA node. Okay? And this is called the AV nodal delay, that little bit of delay between the firing in the SA node and the firing in the AV node. And this is very important because this AV nodal delay, once this AV node fires an action potential, it's going to quickly spread to the bundles of His and the rest of the ventricles. Okay? And it's going to lead to ventricular contraction. So we actually want a little bit of a delay between the firing of the SA node and the firing of the AV node, because the firing of the SA node is going to lead to the contraction of both atria at the same time, which moves blood from both atria into both ventricles. Okay? So we want this AV nodal delay allows for maximal ventricular filling of blood, because it gives a little bit of time for these atria to contract and help fill the ventricles. And then once the AV node fires, you're going to very quickly get ventricular contraction. Okay. So even though we earlier in the last chapter, we followed the path of blood through the heart and we went from chamber to chamber to chamber. In fact, when blood flows through the heart, it actually tends to flow in these alternating movements where we have both atria contracting at once, followed quickly by both ventricles contracting at once. Okay? And so within a single heartbeat or single cardiac cycle, we have both atria contracting at once, followed by both the ventricles contracting at once. Okay? And then in between heartbeats, right? In between heartbeats, we have a moment of rest that the heart takes. Okay? So when the heart is in active contraction, we call that systole. Okay? We call that cardiac systole. When the heart is in its resting phase, in between heartbeats, we call that cardiac diastole. Okay? So systole involves active contraction of the heart, both atria at the same time, followed by both ventricles. Okay? And then in between heartbeats, we have a period of rest that we call diastole. Okay? Now the cardiac action potential that we just talked about that spreads from the SA node to AV node to the bundles of His and the ventricles. This cardiac action potential is frequently, it's a very strong electrical signal, and it is frequently recorded at the surface of the skin by using a particular pattern of placement of EKG leads or ECG leads. And it involves placing leads at the extremities, okay, at particular positions in the extremities, and then leads at particular positions across the chest. Okay. And then based on this very precise placement of electrical leads, you can measure the signal at the surface of the skin that is it's an electrical signal that's being caused by the movement of the cardiac action potential through the heart. Okay. And so this EKG signal measured at the surface of the skin looks like this. Okay. So this is the total signal recorded by all the leads. So if you notice, we have certain upward deflections of potential. We have some downward deflections of potential. Now the thing to remember about the EKG is we're not recording from a single cell. So an upward deflection and a downward deflection does not mean depolarization or hyperpolarization. That's not what we're talking about. It's simply a change in potential that is being caused by all of the cells in the heart, the electrical activity of all the cells in the heart. Okay? So the EKG is composed of some very stereotypical deflections and then periods in between. So the first thing we see is the P wave in an EKG. Okay? The P wave is a small upward deflection. And then what we have is a short period of no activity, followed by a dramatic deflection called a QRS complex. Okay? And then again we have a period of no activity, and then we have a larger upward deflection called a T wave. And then after the T wave we have a longer period of no activity, and then another P wave. So PQRST, this whole period of activity, represents a single heartbeat. So what are the PQRST waves reflecting? The P wave in the EKG, the P wave represents the depolarization of both atria of the heart. So when the SA node fires its action potential, that action potential depolarizes both atria, and you record a P wave. Okay? Then we get this brief period of no activity, and that's followed by the QRS complex. This brief period of no activity is sometimes called the PR interval. Okay? The PR interval represents the AV nodal delay. It represents the delay between the firing of the SA node and the firing of the AV node. Because once that AV node fires, that action potential quickly spreads to the bundles of His, and we get a QRS complex, because the QRS complex represents the depolarization of both ventricles. QRS complex represents a depolarization of both ventricles. Then we have a brief period of no activity, the ST complex, excuse me, the ST interval, and then we get the T wave. And the T wave represents the repolarization of both ventricles. Okay? It's the repolarization of both ventricles. And then between the S and the T, this ST interval, okay, is during this period of time we have ejection of blood from the ventricles. Okay. And then the interval between the T wave of one cycle and the P wave of the next is sometimes called the TP interval. And this TP interval represents diastolic time. Okay. It's the period of time in between each cardiac cycle or heartbeat. So P wave is the depolarization of both atria once the SA node fires. Then you have this AV nodal delay that you can that was reflected in the PR interval. Then the QRS complex represents the depolarization of both ventricles. And then the ST interval represents ventricular ejection of blood. And the T wave represents the repolarization of both ventricles. And this represents the electrical activity of the heart measured at the surface of the skin.